Hey everyone, this is Ken. In this video I'm going to show you what are antiderivatives and also what is an indefinite integral. So the definition of an antiderivative is the following. So you start out with a function and what is its antiderivative if it exists. So an antiderivative for a function f that's given to you. So an antiderivative for function f is any other function, call it capital F, with the property that its derivative is equal to what you started with. So let me show you a bunch of examples. So here's the function. And here's the antiderivative. So I could start out with x, and an antiderivative is going to be any function whose derivative is equal to x. And so one such function is x squared over 2 plus 1. Because derivative of x squared over 2 plus 1 is going to be 2x over 2, cancel them out, and derivative of 1 is equal to 0. So the derivative of this just gives you x. So there's an antiderivative for x. Let's take cosine of x. What's an antiderivative? I need a function whose derivative is cosine. That's going to be sine of x, or sine of x plus any constant will give you cosine of x as a derivative. What about 1 over x for x bigger than 0? An antiderivative of a function whose derivative is 1 over x, I could take natural log of x, no problem. So antidifferentiation, it's like doing a derivative, but in reverse. That's why it's named that way. And one thing you're noticing at this point is that given a function, there's lots and lots of different antiderivatives, because you can just take any antiderivative you start with and add a constant to it, and they'll still give you back the same thing. And so the question that you might ask is, can you get antiderivatives in any other way than by just adding a constant? And it turns out that that's not true. Really, if you have an antiderivative, the only way you can get another one is adding a constant to it. I can show you that with a little mathematical theorem, and here's what it says. It says that if f and g are two antiderivatives of the same function, so say they're antiderivatives of f, meaning that the derivative of capital F is little f, the derivative of capital G is little f. Then f and g must differ by a constant. So f minus g must be equal to a constant. And so how can we do this? Let me show you the proof. If I want to show that f minus g is equal to some constant, here's the way I can do it. You may remember that in a previous video, using the mean value theorem, I showed you that whenever you have a function whose derivative is identically equal to 0, so equal to 0 on an interval, then that function must be a constant. So let's look at the function f minus g. Capital F and capital G are certainly functions, so their difference is also a function, no problem. It's a function of x. Let's take the derivative of this function. Using linearity of the derivative, I can break this up over the minus sign. This is equal to the derivative of capital F minus derivative of capital G. And my assumption is that these are antiderivatives for the same function f. So derivative of capital F is little f. Derivative of capital G is little f. Subtract them. you get 0. So without even knowing the specific function that these were antiderivatives of, as long as I know that their derivatives are equal, then the derivative of that difference will be 0. And that automatically implies, it follows by the mean value theorem, automatically implies that you've got this function whose derivative is 0 for every x. Then that function has to be a constant. And what that means, well, you can sort of rearrange this. So what's the constant? I don't know, let's call it c. And if you rearrange the equation, you can show that f, well, then would have to be equal to g plus c. So if you start with some antiderivative g of function f, and you pick some other antiderivative, that antiderivative must be equal to g plus a constant. You can see that happening over here because x squared over 2 is an antiderivative for x. So any other antiderivative must have the form x squared over 2 plus a constant. And there that constant was equal to 1. And taking this into account, we make a new definition. So if we're given some function f, we say that its most general antiderivative is going to be f, capital F, plus c. And so this is when, so I'll write it down, this is the most general, or the general form. Most general antiderivative of f. And here, this is when you have the case that derivative of capital F is equal to little f. So start with a function like x or cosine x or 1 over x or whatever you've got. Find an antiderivative, capital F. The most general antiderivative you say is f plus c, and that's just supposed to remind you that you could add any arbitrary constant and it stays an antiderivative. And then that brings us to our big definition. And I'll come down here and write it for you, which says that what we call the most general antiderivative, another name for that is to say the indefinite integral of f of x dx. It's equal to capital F plus c. So an antiderivative is a single function whose derivative is the original function. The indefinite integral you can think of as the collection of all antiderivatives. Or if you want, you can think of it as just, this most general antiderivative. We notate that just by saying, capital F plus c. And so, for example, the way that you can rewrite some of these things on the chart is you could say indefinite integral of x. That's going to be equal to x squared over 2 plus c. Indefinite integral of cosine. That's the most general antiderivative. That's going to be equal to sine of x plus c, and so on and so forth. And this notation might seem a little bit confusing. So why are we using an integral sign to notate an antiderivative when heretofore we've used the definite integral to just look at area under a curve? There's an answer to that question, and I'll get to it in another video. But for right now, I'm just showing you definition of antiderivative and definition of indefinite integral.